I'm excited to get into section 3.3 with you. We started our first of our derivative shortcut rules with the power rule in the last section, and of course the derivative of exponential functions, but neither one of those are very fun because with power rules, you just bring the power down in front, multiply by any coefficient, then you decrease the power by 1, and with exponential functions, we just say the derivative of any exponential function is that exponential function. In this section, we'll have the product rule and the quotient rule, both of which are a little bit more fun than the just the power rule and the exponential function. So let's go ahead and start off here with based upon what we know. So if I said based upon what we know from section 3.2, and I ask you to take the derivative of y equals x cubed plus e to the x, you'd say no problem. The first one is a power function, so I take its derivative by bringing the power down in front, decreasing the exponent by 1 to 3x squared. And then, of course, as I mentioned earlier, the derivative of any exponential function is that exponential function. Okay, so we get the derivative of a function like this, but right now we're extremely limited in that we have to have all of the terms out individually by themselves before we can take the derivative. What I mean is that as of now, we have no way of taking the derivative of something like x cubed times e to the x. Now, you might think at first glance that, well, why don't you just take the derivative of the first one times the derivative of the second one? Because that rule does not work for derivatives. You can't take the derivative of a product by simply taking the derivative of the first term times the derivative of the second term. So we have to find out some other way to do it. So this is what I was saying up here. You cannot simply just take the derivative factor by factor. In fact, what it turns out that we must do, and I'll prove this in just a moment, is that for functions in the form where you have some differentiable function of x times another differentiable function of x, the way we take the derivative of the combined product is to say, let's take the derivative of the first term times the second without the derivative, plus the first term without the derivative, times the derivative of the second term. So I always like to say derivative of the first times the second plus the first times the derivative of the second. Now, let's go back to that question I was talking about up here, where if I have x cubed e to the x, well, if it's x cubed plus e to the x, I can see, well, the answer is easy. It's just 3x squared plus e to the x. Well, what about the derivative of the product? I'd have to say, well, it's the derivative of x cubed times e to the x plus x cubed times the derivative of e to the x. So I already know how to take the derivative of x cubed. That doesn't change. It's still 3x squared times the second e to the x plus x cubed. Now, times the derivative of e to the x, which is still e to the x. Now, most of the time with these product rules, I will want you to factor your answer to make sure it's a useful answer. And in this case, if you look at your first and second term, you can see, well, they both have a common factor of e to the x. They also both have a common factor of x squared. So I factor out an x squared and an e to the x, and it leaves me with 3 plus x. Now, later on, when we have application problems, like when we're trying to find when a function is either maximized or minimized. Now, we already know that the derivative is the rate of change. So think about what happens if you set the derivative equal to 0. If the derivative is equal to 0, that's going to be at a high point or a low point on your graph, because think about at a high point, once you get up to that high point, it's going to have positive slope all the way up, 0 slope at the top, negative slope on the way down. Same thing for minimums. It's going to have a negative slope all the way down until it gets to the minimum. The point at which it reaches the minimum, you're going to have a slope of 0, and then it's going to have a positive slope after. So we need to be able to set the derivative equal to 0, and it'd be pretty pointless to try to set this function equal to 0 if you didn't at first factor it. So a factored answer is always superior to a non-factored answer. Now, I want to go in and talk about where this product rule came from, because if we don't talk about where it comes from, then it's empty, hollow knowledge for you just to say, oh yeah, it's the derivative of the first times the second plus the first times the derivative of the second. Thanks, John, I'll just memorize that. That's empty knowledge. So let's talk about where it comes from, the proof of the product rule. So what I'm saying here is that I'm going to let some product function, p of x, equal the product of the function f of x and g of x. Now my goal is to show that if p of x is equal to this product, then the derivative of p of x is going to equal derivative of f times g plus f times the derivative of g. Okay, now, whenever I'm trying to prove anything, well, I can always go back to the limit definition of a derivative. Remember, we just say, well, what is the derivative f prime of x? Well, it's f of x plus h minus f of x over h as h approaches 0, that limit definition of a derivative. Well, think about what we have here. If I said, what's the derivative of p of x with the limit definition of the derivative, you'd say, well, it's the y values evaluated when x is x plus h. So f of x plus h, g of x plus h, minus the y values evaluated at just x. Well, that's going to be f of x, g of x. So my derivative of this product function is going to be the limit as h approaches 0 of f of x plus h, g of x plus h, minus f of x, g of x over h. Now, what I'm going to do in this next step, it seems like it's just coming all out of nowhere. And the reason for that, most of the time these proofs, they're actually done in reverse. You look at something and you work backwards. So in this step, you just have to understand, okay, that's a legitimate algebraic maneuver. What I'm going to do is I'm going to add a 0 to the numerator. You know that that's fine, because adding a 0 never changes anything. So I'm going to add an understood 0, a negative f of x, g of x plus h, plus f of x, g of x plus h. Now, I'm adding that to the numerator. I know what I have here is identical to the original limit definition of the derivative. These two would just cancel each other out. Now, the reason I added those in there is they're going to allow me to see something here. In order to see that, though, now I'm going to separate the limit. And again, I need you to understand it's from each step to each step to each step that it's a legitimate algebraic maneuver, that one step is equal to the other. From this step to this step, all I've done is I've added a 0. Now I'm going to say, after I subtract that f of x, g of x plus h, and add that f of x, g of x plus h, I want to distribute that denominator of h into the first two terms and then into the second two terms here. So I separate the limit and I say the derivative of p is going to equal the limit as h approaches 0. Please notice f of x plus h, g of x plus h, minus f of x, g of x plus h, all over h. I'm adding the second fraction here, which is just the third and fourth term in the numerator, f of x, g of x plus h, minus f of x, g of x. Let's see if I can get that a little bit more clear here. There we go. Now, please take a look at this and understand that you could combine these two fractions to work backwards to this step. This step is equivalent to this step. What's the beauty of this step, though? Now you can look at each of the numerator and pull out a common factor. Since I separated those first two by themselves, I can see, well, both the first and second term has a factor of g of x plus h. So I'm going to factor that out of that fraction and just say, well, I have f of x plus h minus f of x over h, and this is all still inside of a limit as h approaches 0, times that factor of g of x plus h. And again, please understand, this is identical to this. This g of x plus h would have an understood denominator of 1, and it would be equal to the previous step. In your second fraction, look at what you can factor out here. Both the first and second term have a factor of f of x. I'm going to factor that out. I'm going to factor it out in front. And I can say, well, when I factor that out, what am I left with? G of x plus h minus g of x over h. Now, At this point, this is where the gorgeousness happens. I recognize, ooh, what do I know the limit as h approaches 0 of f of x plus h minus f of x over h is? That is the limit definition of a derivative of f prime of x. Woohoo! What do I know the limit as h approaches 0 of g of x plus h minus g of x over h is? That's the limit definition of a derivative of for g. It's g prime of x. So I can say, well, gee, then I can go ahead and take this limit as h approaches 0 and say that my derivative of p with respect to x is, and again, remember, this limit as h approaches 0 has been taken. By definition, that is the derivative of f with respect to x. What happens to g of x plus h as h goes to 0? Well, as h goes to 0, that just becomes g of x. So I have the derivative of the first times the second plus f of x doesn't have an h in it, so it's just f of x, times what happens to g of x plus h minus g of x over h as h goes to 0? Well, again, it's the limit definition of a derivative for the function g, so that is g prime of x. And so you can say, well, if p of x is equal to f of x times g of x, its derivative is f prime times g plus f times g prime, and that is the end of this gorgeous product rule proof. To show that it's the end, I write QED, quoterat demonstratum. Now, you're thinking, wow, that was pretty cool. It really is. It's good stuff. But now you're thinking, well, I need to see some more examples because I can't just look at the proof without problems to work. I got you covered. Let's look at problems. So if I say I want you to find the derivative of y with respect to x if y is equal to this product. Now, what I went ahead and did just to show that this derivative rule works is, let's say you wanted to avoid the product rule for some reason. You should never want to avoid it, but hypothetically, if you wanted to avoid it, what you could go ahead and do, like I said here, is you could do the algebra first and say, well, if I don't want to use the product rule, how about I just go ahead and algebraically simplify it, and I'll distribute the x squared through that trinomial, and then I'll distribute the 6 through that trinomial, and I'll get all of this. Now I combine like terms, and I get 2x to the 4th plus 3x cubed. There's 2x squared terms, so that's going to be plus 7x squared plus 18x minus 30. And then at this point, because I did the algebra first, I don't have to use any product rule. This is just power rule now. So you say derivative of the first is going to be 8x to the 3rd. The second is going to be 9x to the 2nd. Then I have 14x to the 1st. And then derivative of 18x is 18. And we know the derivative of any constant is 0. So we get our derivative answer. Now, what would I do if on a test you had a problem like this, if I specifically said, please take the derivative using the product rule? Well, this would only be to check your answer. I would require you to show your work this way if it said use the product rule. And several of your Achieve homework assignments will have problems like this, but it says to take the derivative with the product rule, so it wants you to do it this way. So I can say, well, okay, now when I'm taking the derivative with the product rule and I'm looking at this product, I know it's the derivative of the first times the second group plus the first group times the derivative of the second group. So now that I have the product rule, this is just set up where I need to take the derivatives. Let's actually start taking the derivatives. The derivatives of that first group, I'll get 4x to the first plus 3 times the second, and then plus my first trinomial times the derivative of the second group, the x squared plus 6. Well, we know the derivative of x squared is 2x, derivative of 6 would be 0. So even though I didn't do the algebra first, in order to simplify this expression, you're still going to have to do algebra. So I used the product rule first. Now I need to FOIL out these first two. If I distribute the x squared through that group, I get 4x cubed plus 3x squared. Distribute the 6 through, I get 24x plus 18. Second group, I distribute the 2x through, and I'll get 4x cubed plus 6x squared minus 10x. And now when you gather your like terms, you'll have 4x cubed plus 4x cubed for 8x cubed. We'll have 3x squared plus 6x squared for 9x squared. We have 24x minus 10x for 14x. And of course, we still get the plus 18. So we get the same answer either way. I much prefer, since this is the product rule section, that you do the problems this way. You might check with algebra first and then the power rule. Now, let's go ahead and look at another problem here. And in this one, you might be thinking, well, hey, he's only talked about the product rule. Now he's giving me a quotient. As you and I both know, any quotient can be written as a product. We can bring this x to the numerator if we call it x to the negative 1 power. So that's what I did here. So I said, if I want to use the product rule to take this derivative, I need to move the denominator up to the numerator and have it raised to a negative exponent. Now the product rule says derivative of the first times the second plus the first times the derivative of the second. When I take the derivative of e to the x, I just get e to the x times the second plus e to the x now times the derivative of x to the negative 1. That's going to give me negative 1x to the negative 2. And then if I were simplifying this, because those negative exponents look very sloppy, I'd say, well, this first one, e to the x times x to the negative 1, I know that's just the original problem. That's e to the x over x. Now, this second one, you have a positive times a negative, so that's going to make a minus sign out in front. And then you're going to have e to the x over x squared. I wanted to clean up this answer. I didn't like the two separate fractions. So I said, well, I can get a common denominator if I multiply this first fraction by x over x. That's what I did here. And then when I got the common denominator, I said, well, then I can combine the numerators over that common denominator of x squared. And I got x e to the x minus e to the x. And then you're thinking, well, John, that's not a good enough answer, because when you combine that numerator, then you see you have a common factor of e to the x. You can and should factor that e to the x out, and you get e to the x times the group x minus 1. And then that would be our excellent final answer for that problem. Now, what I want to do before I move on to some more problems is some more proofs. So we did the two-term product rule proof, and I did it with a limit definition of the derivative. What if I said, I want to do a three-term product rule? What if I have a term times a term times a term? How am I going to take the derivative of that? Am I only ever able to take the derivative of two terms? No, certainly not. And so if I look at the three-term product rule, just for ease of notation, rather than calling it f of x, g of x, and h of x or something, what I'm going to do is I'm going to say, let's let a, b, and c be functions of x. And then I'm going to show that if p is a function of x and it's equal to the product of a, b, and c, then the derivative of p is equal to the derivative of a times b, c, plus the derivative of b times a and c, plus the derivative of a, b, c prime. So what I'm wanting you to see here is a pattern. What if I said, I want to give you four terms, a, b, c, and d? You'd say, well, it's the derivative of the first times the other three, the derivative of the second one times the other three, the derivative of the third one times the other three, the derivative of the fourth one times the other three. Each term, you're going to be taking the derivative of one times all the other terms in that product without the derivative. Now, I need to prove that for the three-term case. Okay, the way I prove something is I can always either go back to the limit definition, like I did right here, or here's the nice thing about mathematics. Once you've proven something, and I have proven the two-term product rule, derivative of the first times the second plus the first times the derivative of the second, that's been proven. Well, once it's proven, it can be used as an axiom as in any other proof. So now this can be assumed to be true in any future proof. Okay, So I'm going to use the two-term product rule proof to prove the three-term product rule. Here's how I do that. If I have P of X is equal to ABC, instead of doing that, I could just say, well, by the associative rule of multiplication, I could associate A times B first and then multiply that product by C. Why am I doing that? Because I wanted to set up a two-term product rather than a three-term product. Now this is the product of the group AB times C. How would the two-term product rule tell me to take the derivative of that? I know P prime of X would say, well, it's the derivative of the first times the second plus the first times the derivative of the second. Now I could say, yeah, but within this, you still have a product in this first derivative. So I could say, yeah, I'm going to have to use the two-term product rule again, because what do I know the derivative of A times B is? By the two-term product rule, I know it's A prime times B plus A times B prime. And now all of that was inside this group where I take the derivative. So I can say, okay, now I've taken the derivative of that group using the two-term product rule. All of that group was multiplying C. And in my second group, I can just say, well, it's A times B times C prime. I'll just do that right there. Now, please notice, all I have to do, I've used the two-term product rule, which we've already proven twice. And now I'll just use the distributive property. C distributes to each term in this group, and you'll get your A prime BC plus AB prime C plus ABC prime. Quod erat demonstratum, we have proven the three-term product rule. And now you're thinking, well, okay, that one wasn't really that bad, John. I want to see one that's even more fun. Yes, yes. What about the quotient rule? Ooh. So you might remember on the previous page, I did a quotient problem, and I said, well, any quotient problem, it can be made a product if you just bring that denominator up to a negative exponent. So in the same line of thinking, in order to prove the quotient rule, I'm going to use the product rule. So what I'm trying to prove is that, and for quotient, I'm letting the function q of x equal the quotient of f of x over g of x. And my goal is to prove to you that the derivative of this function is equal to the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator over the square of that denominator. So it's g of x, f prime of x, minus f of x, g prime of x over g of x quantity squared. I've got to prove that. Okay, so here's how I do it. We start off with, of course, what we're given. Q of x is equal to f of x over g of x. And in order to prove it, I can say, well, I've already proven the product rule with a limit definition of a derivative. So how about we make this a product? I could easily take this equation and multiply both sides by g of x. That's going to give me q of x times g of x is equal to f of x. Now I can say, by the product rule, I can take the derivative of that left-hand side and say, it's just the derivative of the first times the second plus the first times the derivative of the second. That's what I've done right here. Derivative of the first times the second plus the first times the derivative of the second. Of course, the derivative of the right-hand side is just f prime of x. Is this a legitimate algebraic maneuver? Absolutely. Remember, whenever we solve equations, you say, as long as you do the same thing to both sides of the equation, it's a valid maneuver. So if this side of the equation is equal to this side of the equation, then the derivative of this side of the equation must equal the derivative of this side of the equation. That's all we're saying right here. Now, my goal is to solve for q prime of x, and I'm trying to show that q prime of x is equal to all of this. So right now, if I want to isolate q prime of x, I'll just subtract the q of x, g prime of x on both sides, and that gave me q prime of x, g of x is equal to what I had on the right, f prime of x, minus q of x, g prime of x. Now, I've got the term that q prime of x was a part of by itself, but now I need to get it all by itself by just saying, well, you got to get rid of the other factor in that term. I'll divide by g of x on both sides. So I can say the derivative of q with respect to x is equal to f prime of x minus q of x, g prime of x over g of x. Now, this is a true answer. That's good. You might think, well, John, you failed miserably. That's not what you were trying to show. No. What's the problem with it? Well, even though this is a correct answer, it's in poor format. The reason it's in poor format, this would be like looking in the dictionary to find the definition of a word and it using a different tense of that word to describe it. You would say, well, that's not very useful. In the same manner, this equation isn't very useful. It's trying to define the derivative in terms of the original function. So I can just say, well, okay, that's not very good. Then I can go back in and say, excuse me, I can go back in and say, well, q of x is equal to f of x over g of x. Please notice that's the only thing I've done in the next step here is I've replaced q of x with what it's equal to, f of x over g of x. But now you might look at this and say, well, okay, again, that's a true statement. What's the problem with it? It's a compound fraction. You have fractions within a fraction. We need to get rid of that. So I can say, well, I need to multiply both the numerator and denominator by g of x, and it's going to get rid of that denominator of g of x here. When I multiply by the g of x in the denominator, I get g of x quantity squared. When I distribute the g of x to both terms here, I'll get g of x times f prime of x, and I know in this term it just cancels out that denominator, so I'm left with f of x g prime of x. And now notice, this is precisely what we were trying to prove. If q of x is equal to f of x over g of x, its derivative is equal to g of x times f prime of x minus f of x times g prime of x over g of x quantity squared. Now, I always like to do a little mnemonic device for these that says the derivative of the quotient rule is low d high minus high d low over low low. And I never forget the order of the quotient rule thanks to that. Low d high minus high d low over low low. And you're like, hey, that's kind of catchy. It is to me. Now, quod erat demonstratum, we got our quotient rule proof done. Gorgeous. Now, if you're thinking, we need to see problems though, oh yeah. Let's look at a quotient rule problem. Now, on this next page, I just wanted to show it doesn't really matter since order of multiplication is irrelevant. Some people like to keep it in the same order as the product rule. And you can think of it as the product rule with the opposite sign in there. You can say, okay, product rule is derivative of the first times the second plus the first times derivative of the second. This is the same thing, except it's a minus sign in the numerator over that denominator squared. But now, since order doesn't matter, you could easily say, well, instead of f prime of x times g of x, why not g of x times f prime? Same thing. And over here, instead of f of x g prime, oh, actually, I keep that order there. I just switch it there. But the reason I like this, and it really helps me out, is because the first thing I do whenever I take the quotient rule derivative is I put that denominator squared down there. And then I remember, oh, okay, that denominator goes up to the numerator times the derivative of the numerator minus the numerator times the derivative of the denominator. And again, this is the little mnemonic device, low d high minus high d low over low low. That's the low low is because you square the denominator if you didn't get that. Now, let's look at the quotient rule. This is a problem that I had us work with the product rule on the previous page, just to show that when the quotient rule applies, it actually makes the problem quicker and easier. So in this problem, if I wanted to take the derivative, first thing I would do, square that denominator. Bring the denominator up to the numerator, times the derivative of the numerator, minus the numerator, times the derivative of the denominator. And then you say, okay, we know the derivative of e to the x is just e to the x, so that first term doesn't change, minus e to the x times the derivative of x with respect to x, which is 1. Then you'd say, well, this is excellent, but we see we have a common factor of e to the x in that numerator. Factor it out, you get your x minus 1 for a really nice answer again. And you're thinking, well, that one's not too bad. It's really not. What if I look at another quotient rule problem here with you? F of x is equal to x squared plus 1 over 2x plus 3. And so This time I'm using the Leibniz notation, df dx. Newton would have just said f prime of x. Leibniz would have said the change in f, or the derivative of f with respect to x. And then I can say, or df dx is fine. When I take that derivative, I square the denominator. That's the first thing I would do. Then I bring that denominator to the numerator times the derivative of the numerator minus the numerator times the derivative of the denominator. Now, this step right here that I'm showing, you can show it if you want. You don't have to, though. So most people, once they get comfortable with these derivative rules, they never show where the derivative is going to be taken. This is an intermediate step here. You can show it if it helps, but if it doesn't help, there's no need to. I'm just doing it as we're learning. And so you can see, oh, okay, he's doing the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator. A lot of students would just work this problem. They'd go directly from here to here when they take the derivative. They'd say, okay, square the denominator. Bring the denominator to the numerator times the derivative of the numerator. They would look at this and say, well, derivative of the numerator is 2x. Boom. So low d high minus high, x squared plus 1, times the derivative of the denominator. Then they'd say, well, derivative of 2x plus 3 is 2. So yeah, you can show this step out, and it's probably wise to as you first start doing problems, but once you get comfortable with it and you're thinking, well, gosh, I'm kind of wasting time and paper showing that step out, you don't have to. You can go directly. This could be your first step. Now, the algebra must be done. You could never leave a sloppy answer like this. Now, sometimes students are confused. They're like, well, I thought you wanted factors. Please understand, nothing in that numerator is a factor. If it's not multiplying everything else in the numerator, then it's not a factor. Sometimes students mistake terms being multiplied as factors. There are no factors in that numerator right now. So you just say, okay, then you need to distribute and then see if anything will factor out. So when I distribute, I get the 4x squared plus 6x for the first group. I know I'm subtracting the entire product in the second. So I can say, well, I'll have a 2x squared, it's being subtracted, minus 2x squared. I have a 2, it's being subtracted, minus 2. Now I gather like terms, the x squareds combine, and I'll have 2x squared plus 6x minus 2. Now, I do notice, and I probably should have also noticed it up here, I do have a common factor of 2 I can pull out once I get to that step. So I did factor that 2 out times x squared plus 3x minus 1. Now, had that trinomial been factorable, I would have certainly factored it. But you can't find factors of -1 that sum to get to 3. So we can say this is our fully factored final fantastic form of the final answer. Please, please, please never physically square out that denominator. Sometimes students think that they're putting a better answer if they do that. It is not. It's an inferior answer if you do that. Just looking at this, I can tell, hey, yeah, but your derivative does not exist if x is -3/2. So your derivative is going to be undefined, which that means you have like a vertical asymptote or something like that. Now, if you would have squared that out and put it as 4x squared plus 12x plus 9, it would have hidden the fact that the derivative does not exist at -3/2. Far superior answer with the denominator squared out like that. Now, next page. If I ask you to do something like find the equation of the tangent line to a function at a certain point. Now, in this case, I only gave you the x value of the point. So somewhere in here, I've had to find the point that's right here and plug -1 into this function to find the y value when x is -1. The first thing I did here, as you can see, is I was concerned with finding the derivative. I'm never able to find the slope of the tangent line at any x value if I don't have the derivative, which gives me the instantaneous rate of change at any x value. So I can say, okay, derivative is going to be, I squared the denominator, bring that denominator up to the numerator, times the derivative of the numerator, and then minus the numerator times the derivative of the denominator. So now I can say, okay, I have my quotient rule set up. It's always denominator times derivative of the numerator minus the numerator times the derivative of the denominator. Or more easily, low d high minus high d low over low low. And then you can say, okay, now you've got it set up. We'll start taking the derivative. Yep. I have my denominator times the derivative of the numerator. Well, derivative of that numerator, that's going to be 4x to the first minus 4. And I know derivative of any constant is 0, so I just get 4x minus 4 for that derivative of the numerator, minus the term in my numerator times the derivative of the denominator. Well, the derivative of the denominator, derivative of x squared is 2x, derivative of 5x is 5, and of course, again, derivative of any constant, 0. So I have my derivatives correctly taken at this point, but now it becomes a big algebra problem, and you got to say, well, I need to take this entire first product and make sure I subtract the product of these two. So I went in and I showed my work here. First thing I did is I distributed 4x through this first group, and I got the 4x to the third plus 20x squared, and then minus, or sorry, sorry. I put the minus 12 at the very end. Of course I did, because I'm just distributing the 4x. I made a mistake and pointed to that. It's 4x times everything over here. So 4x cubed plus 20x squared plus 12x. Yay, everything's right. And then I distribute the negative 4 through it, minus 4x squared, minus 20x, and minus 12. Now all of that is my first product. I need to make sure I subtract from that everything in my second product. So I'll say, okay, my second product, I'll first distribute a 2x through this trinomial. When I do, I get 4x to the third minus 8x squared plus 2x. When I distribute a 5 through that trinomial, I'll get plus 10x squared minus 20x plus 5. Now here's where I see a lot of students make a mistake. They'll forget that that minus sign's there, and they'll only subtract the first term and then do the wrong sign for everything thereafter. You've got to take the product and then understand everything's being subtracted. So now when I do that, I can see, well, my x cubed terms are going to cancel out. I'll have 20x squared minus 4x squared, that's 16x squared, plus 8x squared, that'd be 24x squared, but then minus 10x squared, that's 14x squared. For my x terms, I would have 12x minus 20x, that's negative 8x, but then I'm subtracting 2x more, that'd be negative 10x, but then I'm adding 20x, negative 10 plus 20, so that's going to give me positive 10x. And then my constants, I have a negative 12 minus 5 for negative 17 or minus 17. So now I know my numerator is correct. My denominator I've just left as that group squared all along. I have my correct answer for my derivative. Now, once I have that derivative, I can find the slope of the tangent line at the x value of interest. I can just say, well, all I need to do is plug -1 into this derivative. When I plug a -1 into this, I know my first term is going to be 14. It's going to make this term minus 10, and then I'll still have a minus 17. My denominator would be 1 minus 5 plus 3. That's what I get down here. So I can see in my numerator, I would have 14 minus 27, which is a negative 13. My denominator is -1 squared. That's negative 13 over positive 1, or a slope of negative 13. So I know the slope of my tangent line when x is -1. It's going down with a slope of negative 13. Now, in order to find the point, all I did was I plugged -1 back into the original curve up here. So please notice, when I plug a -1 into this original curve, you would have 2 times -1 squared. That's just 2. Then you'd have plus 4 when you plug a -1 in there, plus 1. All over your denominator, you'd have 1 minus 5 plus 3. That gives me 7 over -1 for a y value of -7. So now I have the point. The point that I needed was when x is -1, y is -7. I have the slope, -13. It's the derivative evaluated at the x value of interest. You plug this into your point slope formula. Y minus y1 is equal to m times x minus x1. So we say, well, that's going to be y plus 7 is equal to negative 13 times the group x plus 1. I distribute the negative 13 on the right to get negative 13x minus 13. We subtract 7 on both sides, and you'll get your y equals negative 13x minus 20. Now, one thing I do want to go ahead and show, it's certainly not a requirement, but if you would like, you can also check problems like this with your calculator. Here's what I mean. If you type this into your calculator, notice I just entered in the fraction 2x squared minus 4x plus 1 over x squared plus 5x plus 3. Now, if I go ahead and graph this out, it doesn't have to be a good looking graph of it. In fact, if I go zoom 6, it's probably fine. Yeah. Okay, so pretty bad looking graph, doesn't matter. All I need to know is what's the equation of the tangent line when x is negative 1. Now, I'm 99.999% certain the equation of the tangent line is y equals negative 13x minus 20. This is the calculator's way of just checking to make sure I didn't make any silly algebra errors. So I'll go in, or calculus errors possibly, I'll go second program to the draw menu. It is not a program, it's on the draw menu. And you're going to say, draw a tangent line. So I go second, calculate 5. And when I do, it's saying, well, okay, you want to draw a tangent line to this curve. Where do you want the tangent line? And you just hit -1 and then hit enter. It's going to draw the tangent line in here when x is -1. And it says when x is -1, your tangent line, now the calculator is having a slight round off error. And the way I tell students to automatically understand that is if you round any value to 3 decimal places, it's going to give you the correct answer. So -13, what's all that? It's having trouble calculating the slope of the curve at that instance. But it's trying to tell you it's y equals -13x minus 20, which matches what we have here. Pretty nice. Okay, guys, that'll do it for this section 3.3. Please let me know if you have any questions. We're starting to get into some more fun stuff, so I'll be eager to help with however I can.